Welcome to this biochemistry lecture on lipid biosynthesis. In particular, we're talking about hormones and steroid biosynthesis. Fatty acid biosynthesis will be in a different lecture. So just as a general review, cholesterol is the important steroid and hormone precursor. It's the parent compound for all steroid hormones. Steroids are produced in the adrenal cortex, testes, ovaries, and sometimes in some peripheral tissues like adipose tissue and the brain. All steroids have this similar structure that you're going to see to the cholesterol molecule. It's a ring. They're very similar. They're not identical, but they're pretty similar. And all steroid hormones are derived from, again, from cholesterol. And the side chains and the slight differences in the ring structure are all that's different. Again, all steroid hormones are lipid soluble. They're not packaged, meaning that they don't have anything that surrounds them. They're basically synthesized and immediately released, and then they go and do their work. All are derived from the same parent compound. Again, cholesterol enzymes produce steroid hormones from cholesterol located in the mitochondria and smooth ER, and steroids are lipid soluble, and so they can freely permeate membranes. And we'll talk about that more in a little bit. They're not water soluble, so they have to be carried in the blood, complex to binding globulins. That is somewhat of a packaging, but generally that's not one of the things that you're going to see as a full characterization when we talk about packaging. Corticosteroid binding globulins, again, carry these cortisol and other sex hormones around in your body, and in some cases a steroid is secreted right next to each other by one cell and is converted to the active steroid by the target cell. So it's just, very quickly. For an example, is androgen is secreted by the gonad and it's converted into estrogen in the brain. So steroids do play an important role in multiple regulatory events, including carbohydrate regulation, mineral balance, reproduction, inflammatory responses, stress responses, on and on and on, mood, etc. And you can see some of the examples here in the adrenal cortex. You have from cholesterol, we can make aldosterone and cortisol, and in the ovary, we make estradiol, which is a form of estrogen. So how do they work? I think this is important because it speaks to how they're synthesized and the importance of synthesis. So a steroid hormone is shown in yellow has a protein carrier. It's going through the blood vessel. It releases that. It can permeate membranes. So it goes into the membranes. There's a cytoplasmic receptor that allows it to rapidly go through the nuclear membrane. And when it gets in there, sometimes it separates and sometimes it doesn't, but usually we get a transcription event that occurs, and then we get translation that makes a new protein. That protein then produces protein and it carries out the event. Again, steroid hormones are very nonpolar, so they have no charges. They easily can diffuse across the membrane, and they will either enter or leave the cell very quickly after synthesis. So that's the important consideration there. Okay, so what are the types of hormones we have? We have progesterone. We have glucocorticoids, which is basically cortisol, and that promotes gluconeogenesis. We have mineral corticoids, which are things like aldosterone. I'm having trouble speaking today. That maintains blood volume and blood pressure. We have estrogens, androgens, and vitamin D. So androgens are things like testosterone, the development of male secondary organs. Estrogen, the development of female secondary sex characteristics and organs. And vitamin D, which is used to promote bone formation, phosphate loss by kidneys, and promotes intestinal calcium absorption. So those are general categories. So what are the sources? What are the sources that we have? Okay, so what we see here, we can either scavenge cholesterol in our diets. We have a free cholesterol level, which you see right there, or we can have cellular synthesis of cholesterol. We have LDL receptors that can uptake it, and then that gives us again goes into free cholesterol, or we can we can synthesize cholesterol with a pathway using acetyl-CoA. It's a de novo synthesis, and it's a multi-step process that involves multiple multiple enzymes. There's a key rate-limiting enzyme called HMG-CoA reductase. There's a negative feedback on that, and we'll talk about that in a minute. High intracellular cholesterol inhibits that de novo synthesis pathway, and the amount of free cholesterol in a cell is it's very well maintained. And so anyway, the cholesterol then can get promoted to steroid synthesis. So we start with acetyl-CoA in that pathway. HMG-CoA leads to mevalonate. That leads to cholesterol. The cholesterol precursor comes again within acetate from cholesterol ester stores in intracellular lipid droplets, or from uptake of cholesterol from LDLs. And so that's basically, again, where we can get our cholesterol, either from the cell, or we can synthesize it de novo, which you see the reaction up at the top. So here is the general cholesterol biosynthesis pathway. We start with acetyl-CoA plus acetoacetyl-CoA, and we're going to end up with HMG-CoA, which you see the molecular structure. That enzymatic reaction is HMG-CoA synthase. From there we go HMG-CoA to mevalonate. That's HMG-CoA reductase. That's one of your important. These two steps here are important in statin regulation. So this, if you're talking about statins, this is where you start to see the effects of the drugs on those enzymes right there to reduce cholesterol production. So then we go to mevalonate to mevalonate phosphorylated. We go to farnesyl PP. From there we can branch out and go to farnesylated proteins. We end up with which have different functional properties. We can go to squalene, lanosterol, and then we end up at cholesterol. Our job today is, and from there we can build up all the steroid hormones, the vitamin D, the bile acids, all sorts of pathways that exist off this. This is the generic cholesterol pathway. The two enzymes that you're going to need to know are the two that we have in red, because those are drug targets and they're important. The rest of the pathway, intermediates you should know, but the enzymes are not important. I know Amanda will probably go into greater detail on that, but this is the important part of what. So the role of cholesterol then is we branch out and we start getting into all of the other steroid classes. So we talked about all the different steroid classes, and here is where you're going to see from cholesterol how everything gets built. So from cholesterol we get into the progesterone classes, and from the progesterone classes we can get into the androgens and the estrogens from there, and then we can also go from the progesterone into the mineral corticoids, and you see all the enzymes, and you can see the structures in this chart, and you can see where even they're manufactured. And so this chart kind of is an important chart for the exam, for you to study and to figure out where exactly all of these steroids are synthesized, and the enzymes associated, and the general structure. So I don't know that you need to know all the structures of these enzymes. There's a few, like cholesterol, I would definitely know. The rest just use as a reference and have a general idea of what's going on in these pathways. Thanks for listening, and look forward to seeing you in the next round.